Philosophy for Our Times is brought to you in partnership with the New College of the Humanities, a university-level college offering undergraduate and postgraduate degrees in the heart of London. NCH pride themselves on offering unprecedented access to a world-class academic faculty. Philosophy students at the college are taught by some of the foremost scholars in the field, and one-to-one tutorials create a personalised teaching experience. Choose your major and minor for a unique combined honours degree and study the NCH diploma to widen your appreciation of the world in ways you never thought of before. Go to nchlondon.ac.uk for more information. Think better. Think NCH. Hello and welcome to Philosophy for Our Times, the podcast which brings you the world's leading thinkers to debate today's biggest ideas.
Most of us think that when lightning strikes or waves crash, that they do so even if we're not there to see them.
This week, our speakers question our role in reality. Does the field of quantum physics mean we need to radically rethink our idea of objective reality?
According to quantum mechanics, the observer is critical to reality. Heisenberg even went so far as to say that in contemporary physics, objective reality has evaporated.
So, should we accept that objective reality has evaporated? Is reality nothing more than an illusion? Or did Heisenberg and most of quantum mechanics get it wrong? Is the world independent of the observer? If so, what does this mean for free will? Our world-famous panel this week are Nobel Prize-winning Gerard, constructor theorist Chiara Marletto, and Oxford quantum physicist Christopher Timpson. Let us know what you thought of this episode and where you think our role in reality is by tweeting us at IAITV. Please do head over to iTunes to give us a rating and review, as we'd love to know what you think. Back now to David Malone, who hosts this week's episode.
Chris, would you like to start with telling us whether reality is there?
Whether reality is there, whether it's necessary. Thank you, David. Yeah, so I take the question here, is reality necessary, to mean something like, to what extent do we as individuals, people like us, or creatures like us with relevant complexity similar to our own, to what extent are we free agents able to affect the course of goings-on in nature, or perhaps even help constitute the course of goings-on in nature, versus everything being fixed up from time immemorial in intensely detailed physical laws which constrain goings-on? Now, with the question of whether and to what extent we play an active role in constructing reality, today I want to argue yes. I want to take the view of a particular approach to physics, to quantum physics, called quantum Bayesianism, or cubism for short, and try and help explain to you how cubists, quantum Bayesians, contract their name to cubists, Q-B-I-S-T, how the cubists would answer positively the question, do we play an active role in constructing reality? So far as that is the case, that reality is not necessary. We are doing something interesting and interestingly different from how normal physics, how classical physics would allow us to be doing. But with the question of constructing, I want to lay down some distinctions to begin with that we may find helpful as we go through. So it seems to me that there are at least three different notions of constructing reality we ought to be interested in here. Maybe there are more, but at least these three will be useful to bear in mind. So I think we need to distinguish between causal constructing of reality, between constitutive constructing of reality, and finally, conceptual construction of reality. So the first of these, the causal construction of reality, is a very humdrum notion. It's the way in which any object which is capable of doing things makes a difference to the world in virtue of its being there. So in the same way that one might construct a house by moving around bricks and mortar and glass and cement and so on, one can construct reality by doing things like moving around bricks and mortar and glass and cement. So it's just a humble idea of our making, or of there being, causal differences in the world in virtue of certain objects being there. Okay, so that's quite a humble notion. Constitutive construction of reality is a different notion, a more metaphysical one, if you will. And it's the idea of there being some kind of metaphysical dependence between kinds of objects. So there might be a something which is causally independent of me, something which I haven't myself made, but nonetheless which exists. And there's a question of whether or not it, such as this table, which I didn't make, does this table exist independently of me? That's a constitutive notion, a metaphysical notion. And finally, conceptual construction, that's to do with our description of the world. To what extent do the concepts that we deploy in physics or in anything else, to what extent are they responsive to a way that the world is independent of any process of concept construction about it, any process of the activities of representing beings? Now, according to the cubists, essentially all the action is on the causal construction of reality. And importantly, the difference here from classical physics is that in classical physics, typically it would be thought that insofar as we ourselves as observers have any role in causally constructing reality, it's a derivative one that's derived from the completely detailed, completely fixed, deterministic laws of the universe that have existed forever or have retained forever, and our activities are merely consequences of the initial conditions of the universe and the changeless laws. The cubists would have it that this is wrong. There may exist emergent, higher-level generalizations which describe our goings-on, but at the fundamental microscopic level, there simply aren't any laws there. And that, crucially for the quantum Bayesians, opens up the possibility of ourselves as agents doing things autonomously ourselves in the world in a way which isn't derived from the laws of nature.
And I'll have to stop you there. Thank you. Chiara, would you like to go next? Do we play an active role in constructing reality?
I would like to give a little bit of perspective after Chris's explanation about all of these different ways of thinking about this question. A perspective on how a physicist would consider this question about reality. So it's a bit like, you're faced with a tiger. The tiger shows up, and of course you could wonder, is this real? But you don't want to take a chance, and so it's better to think fast and find a problem, solution to the problem. So try to get out of the way. And so likewise in physics, the way I feel about this question is that really it seems we are facing problems all the time. And these problems are basically gaps in this conceptual understanding that Chris was mentioning of reality. And we're trying to solve them. And so in that sense, I think we are constructing something. For instance, we were wondering at some point in the past, how come it looks like stars are moving in the sky and the sun looks like moving in the sky, etc. And we were trying to fit that into our understanding that maybe the Earth was at the center of everything, and that didn't work at some point. So that was a problem. It's like the tiger. So the question of whether reality is really out there is somehow secondary in this context, because what we seem to be worried about is how to solve problems. And the solutions that we come up for these problems are these theories that we have about reality. Quantum theory is an example. There are lots of others. And these theories are something that we construct. So it's kind of every time someone comes up with a new theory, there's new knowledge in the world. And this is something that we use in order to make tentative progress. And I think this is, for those who like philosophy, this is a bit of the view of Karl Popper's. Now, this is possibly, I think, the most honest and compatible view of reality that I see from the point of view of physics. So that's my take on this question.
Okay. Gerard? What do you think?
Yes, I'd like to state my answer to the first question right away. I say, of course not. Reality is, it's one of the great accomplishments of science in general, that we have discovered how the reality around us actually can be explained and how things behave according to laws of nature. But now, of course, we have quantum mechanics, and quantum mechanics seems at first sight to put everything upside down and say that there's vagueness and so on. But I think you have to make a very clear distinction about vagueness of the world that we are seeing around us and the vagueness in our way of describing this world. So physicists haven't yet done their job completely. They've only found a partial solution to the question, why are the laws of physics the way they are and what's happening? The answer is we don't know, but the best we can do is make predictions, and our predictions are vague. If you see every day the weather forecast on television or whatever, you see that they have certain percent chance of rain. Here it was 100% chance of rain. Normally they say any certain chances of rain, chances of sunshine, and so on. We aren't sure because our theories are imperfect. Of course they are. The universe is far too complex to say things anything better than that. But now I come to a very important point. I say, if you believe that the world is realistic, that the laws of nature are only about real things happening, you have to take that all the way. Because when we have discussions about the subject, very often people say, yes, but don't we have free will to do this and free will to do that when we measure things? As soon as you say that, you say, wait a minute, free will, what free will? Free will is also determined by deterministic laws of nature. We don't know those laws. Of course we don't. We are human. We have all our limitations. We can't predict how fast you are breathing this moment. But it's all fixed by laws of nature, and we should find our task as physicists, it should be to figure out what these laws are as accurately as we can. Today's most accurate theory is called quantum mechanics. So yes, I'm very sorry, but every now and then we can't predict things with certainty. That's because our models are failing, because our models are very good, and in practice the predictions we can make are fantastic, but they're not perfect. So that we have to take into account. Then the question of qubits, the question why we even have qubits, well, it just tells us how bad our understanding is. We can create vagueness in a very complicated way, and this complicated vagueness is called entanglement. Even that can happen, which means that we still have a long way to go to understand those deterministic laws. In fact, I think we are being misled by the fantastic features of mathematics. Our world seems to be described by fantastic mathematical equations. Mathematicians can handle this kind of uncertainty. They call these non-commuting numbers. And not only that, in mathematics, we can describe entangled states very, very well. And also, mathematics tells us there's a fantastic symmetry in this world. Our problem is the symmetry is much too large. For instance, particles can only sit in certain orientations. An electron can only have two orientations in this world. That is very strange, because you would think that you could rotate an electron any way you like and you get another rotation. How come that particles can only have two orientations? Well, that's called symmetry. There is rotation invariance in the world, which is a true property of the mathematics, but it is not a true property of those realistic states which we eventually want to describe. Again, this means that there's lots of work to be done. Why is this so important, this question? Because in the Copenhagen discussions people had at the time, the outcome of the discussion was, don't ask such silly questions because you cannot check it experimentally. That is true, but that's not a good argument, because you can still to investigate realism is very important for our question of model building. Our models of the world today are imperfect. That's why they're quantum mechanical. But to improve that, we need to have some lead. And one of the leads that we want to use is, suppose the world is completely realistic. What would that do to the models that we have today? How can we improve our understanding?
Okay, so I think it's worth just pressing a little bit more on the role of the observer, because classically what everyone gets taught is that at the macro level, you sit on the outside of events. You don't have any effect. If the table falls off, it's not because you thought about it, it just happened. Whereas at the quantum level, there has always appeared to be this, the observer has an effect, that when the observer observes, the cat's either dead or alive, but was possibly both up until then. Are we saying that view, which is what turned physics upside down when it happened, that we now say, no, that's completely wrong, that there is no magical cat which might be dead or it might be alive, and are we saying that that's wrong now?
I think that's where Gerard wants to take us.
Yes, Gerard certainly does. Chiara, I'm not sure.
Not really, yes, but yes.
But so let's press that question a bit further. So on the one hand, we might say, yes, whatever theories we have at a given time, even if they're our best established theories, the best we're working with, perhaps there's some successor theory which will have some other features than the current theory we're looking at. So that's one thing that we're being urged to look at by Gerard. And it could be that in whatever the successor theory is, it's business as normal with regard to the status of the observer vis-a-vis the rest of reality, something like a return to classical physics. Well, maybe. But the question is, on what basis do we make that judgment? And it doesn't seem to me that things need be like that. Maybe it would be nice if they were so, but maybe we can actually be more excited by what, if you look at the content of many general claims that we would take to hold given quantum mechanics' predictive success, that in fact a more natural thing to think is that there isn't any more fundamental, microscopically non-vague, complete theory to be had. What do I mean by that? We have the process of looking at the general claims made by quantum mechanics, or looking at the confirmed experimental predictions, formulating a yet more general theoretical scheme in which these can be embedded and explained, and then drawing conclusions about what further kinds of theories could possibly produce the results that we've seen in experiments. These are called no-go theorems and no-go experiments in quantum theory, where you're trying to pin down not features of quantum mechanics itself, but features of what the world itself needs to be like in virtue of the predictions of quantum mechanics being confirmed experimentally. And it seems to me that the output of these theoretical and experimental results is in many ways very naturally explained by saying there isn't a fundamental completion, there isn't a fundamental set of laws at the microscopic level describing everything which behave in much the way that physics traditionally has taken it to do. And what's the problem with that? So I want to ask you, Gerard, why the insistence for this atavistic notion of the underlying physics?
Well, I find that all alternatives are much worse. So I think the best of all possible worlds that I can imagine would be a completely deterministic one. And once you say partly deterministic, then you fail completely. When you say, okay, deterministic, but in Bell's famous Gedanken experiment, Bob and Alice still have the free will to choose their orientations, then I say, wait a minute, now you're violating something, and now you're putting yourself in a difficult position. And if you look very carefully at the mathematics, I claim that Bell didn't have his definition of causality correct. So causality to him means that the future will not affect the past, but the past will affect the future. That sounds reasonable, but it isn't. In our models, yes, but in the world, as soon as you change anything in the present, you must have that preceded by a change in the past. Otherwise, a change couldn't have happened. So the problem that Bell was struggling with was that he didn't want to change the past, but he didn't want to change the decisions that Bob and Alice make to measure something. That is forbidden. And that itself is a very strange thing that makes it very hard for us to make models which show that. So Bell thought, because of his arguments, those models are impossible. And I claim, no, we haven't searched hard enough, but I don't think they're impossible.
So, you're wanting to say that quantum mechanics may have appeared to its discoverers and the generation of science afterwards to involve this sort of randomness, if you like. But you're saying they just need to peel back that layer, and underneath there will be some rules which are deterministic, which are like the rules up here.
You have to actively search for that. If you don't do that, you'll never you never do such a thing. For instance, you get string theories, but string theory is also fundamentally quantum mechanical. So this is why I have my doubts also for string theories.
Well, you're not alone
they're not there yet, not by a long way.
Now, are you finding with this theory for us?
There are lots of things to say. So the one important thing is that we mentioned the observers. Now, usually there is this capital letter O in front of observer, which is kind of perhaps misleading in the sense that, as far as I understand, quantum theory is very democratic in regard to observers. That means that basically, if you just consider what quantum theory tells you about an electron interacting with another electron, you can in a way describe in the same way the way an observer such as a macroscopic observer such as you, for instance, interacts with a measuring instrument, which is also macroscopic, which then interacts with something that's less macroscopic and less macroscopic, etc., up to the point where you hit the electron. So I'm not in agreement with this view that kind of singles out observers as special entities, because it seems to me that unless you add some postulates on top of quantum theory itself, there isn't any such distinction within the theory. And this is actually the beauty of the theory, because it leads us to think of what would happen if an observer such as you were to be superposed across different states of, for example, consciousness or things like that. Of course, we can't do that now, but it's a nice thought experiment, and it would be interesting to consider that. I just wanted to say that, therefore, when we talk about observers, we have to probably, we three of us have different views about what that means. And in my case, I don't regard an observer as an entity which is that different from an electron which interacts with some other system.
Can I ask you, because you've raised the observer as being important, surely quantum mechanical things were happening long before humans evolved, or were cats, before we came along, always not quite sure if they were alive or dead?
Good. So, I mean, this is an excellent way of probing exactly this kind of question about the role of the observer. So when I was stating the kind of view, the cubist view that I want to explore today, I did allow that there could be law-like claims, generalizations about macroscopic kinds of objects. So it's only really when you sink down that quantum effects are becoming very salient that you begin to lose the laws, that you lose the law-like structure underpinning things, and you're left with a sea of entities having causal powers, modal powers, abilities, dispositions to do things, but not falling under any well-organized set of physical laws. So that's consistent with all the macroscopic stuff, dinosaurs and all the rest of it, having existed, stars, having existed for an awfully long time, because it's business as usual for large stuff. The surprise in this approach is that it's not business as usual when you look at the small stuff of which the large stuff is supposed to be made. So we can completely recover our intuitions about what the structure of the past was like, insofar as we ought to have determinate intuitions there, namely at the level of the things which are roughly familiar, big, fairly big stuff, but also fairly small stuff. So you should probably be able to get most of biology to come out, if you ignore the details about how chemical bonding works.
Thank you for that. I feel reassured. Why is it that this theory, which everyone has signed up to for the better part of a century, everyone accepts it, but nobody shares the same theory? We've got many worlds, we've got hidden variables, we've got don't ask. Why is that? I mean, if any other theory had such wildly different interpretations, humble biologists like us would say, well, you don't have a theory, but you all think you do.
There are different ways of interpreting the theory. So you've got the mathematical framework, and then you're asking yourself, how are we to understand this? What's the world like if this is a good mathematical description of it? There's a good deal of the content of the theory which is insensitive to what particular philosophy, if you like, you take to it. And that's most of what you need for deploying the theory in most experimental situations, not all of them. One of the things that's slightly strange about the debate with quantum theory is that we forget how weird classical physics is. Right? Classical physics is supposed to be non-weird. Classical physics is deeply, deeply weird. And it's an excellent education to think, what is a point particle? There's no such thing as a point particle, yet that's supposed to be what Newtonian physics is about. Isn't actually the idea of a point particle literally incoherent and collapses in Newtonian physics or in Maxwellian physics if you push it too hard? So these kinds of questions are rife in any bit of physics. In fact, in many bits of science more generally, you can always ask, well, really, what's going on here? As well as having the day-to-day practice of deploying the theory in very skilled ways. It's just that we haven't had a successor theory in the last 100 years, which has made us stop asking these kinds of questions about quantum theory. And it's a theory where it's hard to push it to levels where it's easy to see where some of these different philosophical points of view would make an experimental difference. So such things are possible and do exist, but it's an experimental challenge. Some are very distant challenges, some are more nearby, to push things into a realm where we can look at that. So this is richness rather than poverty of understanding.
Yeah, I was just wanted to say that I think one of the reasons why this is happening is that all of the existing interpretations agree on what is accessible through experiments at this time. So what our technology can experimentally probe. The predictions of all these various ways of looking at quantum theory are the same, and they ought to be the same, because otherwise it would not be quantum theory, it would be a different theory. There are proposals for a different theory. So there are these models that are called collapse models, where the idea is that there is a specific scale at which quantum theory fails. So those can be tested against quantum theory, and we are getting closer and closer to testing them at larger and larger scales. However, as far as interpretations go, given that their interpretations can be tested with respect to one another. So that's possibly one of the reasons why this is happening. And it's connected to a particular feature of the theory, which is that unlike classical physics, and that's perhaps why we're not wondering about classical physics as much, unlike classical physics, what quantum theory says is that there are features of a physical system that can be accessed just by looking at it once. So what you can do is that you can prepare systems, lots of copies in the same state, and do lots of experiments the same to figure out what's going on and get an overall picture and the complete picture. But if you just limit yourself to single measurements on a single system, you can only get some partial information. So there are some empirically inaccessible features. And those are the ones about which interpretations differ. And as far as I'm concerned, I think there was only one interpretation, which is many worlds, but that's just me.
Really?
Other
You're
than
a
that-
many worlds person?
Well, I think that's the one that makes the most sense.
See, it doesn't make any sense to me, but then...
Well, yeah, because the others are even worse. So, I have to go with what is there. So.
So it's like the argument for democracy. It doesn't work, but it's still better than the other stuff.
Yes, it's a good working assumption, yes, I would say.
But Gerard, do you obviously don't go for the many worlds.
Absolutely not.
Why not? Why?
I was thinking about the previous question about why there are so many interpretations, and I think the answer is that the actually correct interpretation is very difficult. So Einstein was quoted once to say that the dear God is very refined but not malicious. In quantum mechanics may be very close to being an exception to this, that the truth is very difficult to fathom, whereas it's much easier to make some simplifications which are actually wrong. I had an uncle, a famous theoretical physicist in Holland, who used to say that about many things there's only one truth and there are many lies. So in a democratic world, the lie will always win. And he was not very optimistic about humanity's future. But I think it holds in quantum mechanics. There's always something wrong with whoever comes to the interpretation that is not like saying that there's simple reality and that's it. And that's the only one left to me where I can't say there's something obviously wrong with it.
Right, but I mean, I think I'm right in saying that Einstein. Some people have said to me, Einstein didn't believe in quantum mechanics. That seems to be silly. I think what he said was, quantum mechanics is obviously true. I just don't think your theories are right. So would he be on your side,
Yeah.
or would he?
He'd be closer to Gerard's
Yes.
Right.
view.
He just felt that the theory, as Heisenberg and Bohr came up with it, was just obviously not right.
Well, it was predictably right, but he felt that it didn't have the overall correct theoretical shape, and he was interested in something like a hidden variable kind of completion, but not of an ordinary kind.
Okay, you can't say hidden variable without telling people. So this is one of the various interpretations. Is it fair to say that hidden variables is making a comeback? Because it is a matter
Well, it's been ruled out
of fashion.
experimentally, but
I mean,
yeah.
in
Never
fashion
mind.
for us is flared trousers and kipper ties. For this lot, it's many worlds or hidden variables. Or is hidden variables coming back? And can you tell them what it is?
I think it's
Or one of
probably so you used the word hidden variables right at the beginning without explaining what it was. So I'm just following your lead.
Oh, okay. Don't blame me. I'm a biologist.
Right, so the idea of a so-called hidden variable is that if you take the normal mathematical descriptions in quantum mechanics, it doesn't seem to tell you all of the things you think that might be said about how the world is. And the idea is there might be some actual variables in the world which we're not seeing, hence hidden, which do fill in all the details. So there's no vagueness, perhaps, because in fact there is a more specific description that's going on underneath. It's just one that we're ignorant of. So I think it's fair to say that in some ways Gerard's preferred option for surpassing or completing quantum theory would be a species of hidden variable theory, but one which is relaxed about backwards influence in time.
Is that?
But in terms of making a comeback, I think with all of these interpretations, collapsed hidden variables, there are probably increasing numbers of adherents of all of them, because we're actually understanding what's involved in them better. And in some ways, it's quite good to have a plurality of views. You've got serious people seriously developing them. In both the hidden variables program and collapse programs, you've got genuine physics to do as well as just philosophy. So you actually have to show how these things could be completed in various ways to work in high energy physics and so on, in particle physics. And whether or not ultimately they're successful is probably down to whether or not you can get those kinds of models to work, to build. So it's basically a kind of a physics question, not a philosophy question. But I think there's more of everything, and that's surely a good thing.
Surely. Can I move on to the third theme, which is what would be the consequence if the hidden variables is right, or if the collapse is right? Does it make a difference in how we see the world and how we feel we work in it? I mean, is it just a matter of free will, or do other things come and go?
I think it's absolutely so. The one objection I have against the hidden variable theory is its name. I don't think the extra variables are hidden. They are just difficult to see. And because 99.9% or more of this world is hidden, because we can think of particles accelerating to much higher energies than we can ever make, and the quantum states they will be in are partly hidden, but we have no access to that kind of information. So these are variables to which we have no access today, but it doesn't mean that they're hidden for any fundamental reason other than saying we cannot see them because our experiments are not good enough to do that. But then in the very end, I think if we keep this in mind, the theory that there could be such a thing as hidden variables, let's try to make models which take them into account in a very natural way, then I think that would be a big advantage. And we have some lead to hold on to make our next best theories for reality.
Well, I still want to push on this question of, so that we can all understand, does how we think the world works change fundamentally if you're right? I mean, do we all have to go, there's no such thing as free will, or?
I think the answer is yes. No. Not so much that that we are now dealing with quantum mechanics and that the world of the atoms and the fundamental particles and the photons will be any different. No, it will be the same world we'll be talking about, but in the very end you'll have an explanation that's completely natural in terms of ordinary physical processes which do not know anything about quantum mechanics. The suspicion I have is that ultimately the laws of nature that describe some sort of theory of everything would be laws of nature where the word Hilbert space, the word quantum mechanics doesn't occur. But in working out the equations, see now what is the consequence of this theory for our daily lives, we have to switch on quantum mechanics not as a belief, but as a mathematical procedure. Mathematicians use such procedures already long ago. So they are working with vectors all the time. For them, it's very ordinary to do so. For physics, we also want to interpret what these vectors mean. And my claim is they mean nothing. They display your ignorance. But it's much better because look, there are 10 to the 40 or 10 to the 80 or something protons in the universe. How can you ever think that we can control and understand every single one of them? Of course we don't. So we have to make all sorts of approximations which are statistical of nature. And the best approximation we'll then discover is called quantum mechanics.
Okay. Do either of you two feel like rescuing because if I've understood you right, we would have to say we think we have something like free will, but it's not true. So we're creatures who are automatons in some respect, but programmed to think they have free will. Are either of you two going to rescue us from this? Because I don't fancy that, really.
Well, I'm afraid the question of free will is actually way above our heads in the sense that
it's above your pay grade.
No, I mean what I meant is that so in any of these interpretations, many worlds, even collapse, there is just one. At least in the case of collapse, there's just one path that the universe goes through. So even though even if you relax this hidden variable idea and you go into the collapse interpretation, what happens is that the history of the universe can be collected into a sequence of such collapses, but it's just one trajectory. And even though there is some stochasticity in it, that doesn't mean that necessarily that there is space for free will. So that also doesn't necessarily rescue free will.
And that's one of the reasons you might want to come over to the cubist side of things, because they say it's a different...
I knew there was a reason we had to hear.
They've got a different game. They say, look, so there's enough structure and goings on that you can put your cup on the table and it not fall through, but there isn't an underlying set of laws which are determining what you're doing. So in cubism, I mean, if one's worried about the questions of compatibility between determinism and free will, or even between the obtaining of physical law and free will, then cubism gives you a robust way of getting out of it, because you, like many other objects in the world, are autonomous and possessors of causal power, and you can make a difference, and you're not just deriving that difference-making from the laws and initial conditions. So there is genuine scope here for something different.
Is there a cost to that? If I sign up to that, because that sounds great, I get to decide where I go on holiday. It wasn't predetermined. But do I then have to sign up for that? If I close my eyes, you all disappear?
No, I mean, and that's a good point, right? So this comes back to the causal constitutive business I mentioned earlier. So it's not the case that other things in the world, their essence, if you will, or their existence, better, is constituted by engagement with me. That's not part of the cubist picture. It's rather that you've got a something which has its capacities and powers. You've got a something else, me, maybe, which has got its capacities and powers. They bump into each other and react in a certain kind of way, which isn't governed by any detailed law at the microscopic level. But this thing still exists. This thing still exists. You all still exist if I close my eyes and stop my ears, you'll be glad to say. So it's not a solipsist kind of program, just asserts that there are fewer physical laws than you thought there are, and that the physical laws that there are go into less detail than you thought there is.
I think that sounded good. Please.
There's just one more thing to say, that it's nice to know that both the collapse view and the hidden variable view are somehow conservative views, in the sense that they try to rescue this classical picture of the world, which is so dear to us because that's what we see directly. And the reason why actually I like many worlds is that it's actually the genuinely revolutionary and new thing in quantum mechanics. So there is a different camp from the one that we just heard about, where physicists are betting that the next theory is going to be even more wild than quantum theory, and it's going to surprise us in even more ways. So most of these features that quantum theory can power, such as even quantum computing and so on, depend from these other wild features that more conservative ways of looking at quantum theory would like to reduce to some classicality. And I would like that not to be the case. I would actually like to be that the quantum theory is as wild as it seems to be. I'm hoping also the search for the next theory is informed by this view, and that the next theory is going to be even wilder.
And I think that's a great place to end. I know we've only scratched the surface.
I just want to mention that there are also loopholes in the theorems.
There's
Yeah.
a loophole in every theorem, yeah.
Well, it just remains for me to point out the last loophole, which you can close, which if you'd help me thank our panelists, please.
Thank you.
Thank you for listening to this week's episode of Philosophy for Our Times. This podcast is brought to you by the Institute of Art and Ideas. It was hosted by me, Anna Carey, and our guests this week were Gerard Hooft, Chiara Marletto, and Christopher Timpson. As ever, we'd love to hear what you thought, so please do head over to iTunes and leave us a review and a rating. Subscribe today to make sure you never miss any of our episodes. And of course, tune in next week for more debates and interviews from the world's leading thinkers on today's biggest ideas. For more debates, talks, and interviews, subscribe today to the Institute of Art and Ideas at IAI TV.